I'll just get started. Okay, how is everyone doing? It's been long. Good morning. My name is Christine Simpson. I'm an assistant computational scientist in the data science group here at ALCF. My background, just to mention, is in computational astrophysics, but what I do here at the facility is I support workflow tools. So I'm going to talk today about some workflow tools, and this is going to be a little bit more interactive. So we're going to look at some code, we're going to run some things, and hopefully you can learn about sort of a range of tools that we support here at the facility. And I will say, I'm going to talk about a few tools. Of course, there are many tools out there, and if there is a tool I don't mention here, that does not mean you cannot use it on our machines. Of course, come talk to us and we can help you if there's something here you want to use that I didn't mention. So let's just begin by orienting ourselves. Everyone has a workflow to some degree, like you have a set of steps you take when you log onto the machine to run code and achieve a result. But what is a workflow tool? So what I mean when I say a workflow tool is it's a piece of software that orchestrates the execution of large numbers of tasks on compute resources, handling things like dependencies, data flows, errors, timeouts. So just, a human cannot orchestrate all of this by hand by just typing in a shell, let's just say. So what a workflow tool can do for your workload? Well, it can run many tasks concurrently and or one after another asynchronously across one or maybe many batch jobs. It manages task dependencies. It can automate error handling and restarts. And it can manage data movement if you need data packets moved onto the file system before a task starts. So this is just a little figure from a paper using a tool that I'll discuss today, Parcel. And they use this tool to manage a workload that generated synthetic sky images for astronomical surveys. So ALCF and ANL have developed a number of tools at the lab, and also we have a close partnership with Globus Labs. And I'm going to be talking about some of the tools that all of these groups have developed and used at the facility. So today, I'm going to be talking about three tools: Parcel, Globus Compute, and Balsam. So Parcel is a code that is developed by Globus Labs, but they have developers at UChicago and ANL. This is a Python-based tool, and it's a particularly good choice for locally executed high throughput workflows that maybe execute tasks on maybe single nodes or single cores, although they are developing more in the direction of multi-node MPI tasks. Then I'm gonna switch gears and talk about Globus Compute. This is also developed by Globus Labs, as the name suggests. And this tool was formerly called FunkX. So if you've ever heard about FunkX, that's what this is, but they've rebranded. And then this is a tool that is designed to execute tasks remotely. So I'm going to demo how I can run a task from my laptop on Polaris through the Globus service using Globus Compute. And then the last tool I'll talk about is Balsam. This is a tool developed at ALCF within the data science group, and it's been at the facility for many years. It's a particularly good choice for deploying multi-node MPI jobs on our machines. Like if you're running, 100,000 instances of VASP on 2 to 10 nodes each, like Balsam is a good choice for a workflow like that. It works on a database model, and so it's actually the only tool I'll talk about today that is really a database model tool, and that's for some people and not for other people, I'll just say. So I'll show you how that works, and this tool can also, because it works with a database that is hosted remotely, this tool can also execute tasks remotely. So this is just a little overview of what we'll be covering. So I'm going to begin with Parcel, and as I mentioned, this is a Python-based tool, so it's a parallel programming library for Python, basically. So you can install it simply with pip. If you have a Conda module or you have a Python virtual environment, it can execute functions that are both Python native code, but it also can wrap around bash commands. So any compiled executable written in any language can be run with Parcel. One thing that takes a little time to wrap your head around about how Parcel works is apps, instead of returning like the result directly, what they return is a Python future, and I'll talk about this in more detail. You can think of the future as being basically a proxy for a result that may or may not have yet returned. So what Parcel does under the hood is you tell it, run this function some number of times, it returns to you a bunch of futures, and then it goes and it has a set of workers that it knows about, and it starts running those tasks on those workers. But until the worker has executed the task, the proxy, the future, hasn't been fulfilled. So the future will exist as an object, but it won't have a result attached to it yet necessarily, and we'll see examples of this. So you can run, apps concurrently or with dependencies, and it's a large development community. They have over 70 developers, many at U Chicago, A&L, and they're a part of Globus Labs. So this is just discussing a little bit the concept of futures. So there is a Python library called concurrent futures, and Parcel is like an extension of that, designed to leverage it to execute work on HPC machines and other kinds of machines, cloud services, et cetera. So as I described, these apps will return a future object. And so here's a little example. This is a little function. It computes, doubles a number and returns the result. And it has this decorator on top of it, Python app, which tells you that it's a Parcel Python app. And when you call it, what these variables D1 and D2 return is not actually like 6 and 10, it's the future. And so what then happens is, in a normal Python code, these would execute serially in this code. Instead, what happens is you create these futures, they get sent off to Parcel workers, and they can execute concurrently. And here, this print statement that prints the results of D1 and D2 is a blocker on the code. So the code, like you create these futures, they go out and fulfilled, and then you need to include something in your program that will wait on the results for them to be returned. And so that's what this print statement does. You can also create tasks that are dependent on one another. So if you have, again, double, and then you're gonna pipe the result of double into another function, square, that will then create a serial chain of tasks executing, okay? So like this future cannot be created until the result of the previous future is returned. So we sort of chain results like this. Okay, so now I'm gonna switch gears and hopefully this will all work smoothly. So, well, this is the schedule, and this is the repository for the workshop. So if you go to the GitHub repository, there's a whole bunch of examples for all the different sessions, and we're gonna go to the workflows one, and we're gonna click on the Parcel one, and we're gonna just go through some code here and look at some examples. So I won't go in depth into the setup. There is, I should say, a workflows session virtual Python environment that is located in the workshop file system space. So you can just activate that, and it should have all the packages for all of this installed, but you can install yourself. So here's like a little example showing you, I mentioned the different types of applications that Parcel can execute. There's a Python app, which will just execute native Python code. This one just executes, it just returns a message, a string. And then you can also run what's called a bash app. And so to distinguish the two, you have to include a decorator telling it whether it's a bash app or a Python app. And what this will do is whatever string is returned here, it will execute this as a shell command. So this is just running echo, but it could be, my program exe, it could be any compiled executable. Then here we have this print statement that waits on the result of the Python app. And then we have here a statement just calling the result of the bash app. And one feature about the bash apps is that they can only communicate with one another through files on the file system. So that's one limitation that you should be aware of when choosing Parcel. So we have to wait on the result, and then we can open the standard out that was printed to the file system, and we can print it out. And so if I'm on, can I move this? Let's move that down there. I'm on the file system on Polaris. I'm in the workflows directory. Oh, my shell is frozen. Thankfully, I have a backup shell. Let's go to Parcel, and we can just, so you just run a Parcel program like this just with running Python. So I have my environment loaded, and we'll just run this, and this is just going to execute on local threads on the login node. Hopefully it will return. Okay, there we go. And you can see it just printed hello world and hello for Python and bash. So I didn't describe too much how it knows what compute resources to run on, you'll notice. So I sort of skipped over this command here, parcel load. And this is where the magic happens, where you tell Parcel what resources to assign to workers. So every worker in a Parcel program will run one task at a time. So you have to tell it, okay, I want 100 workers, 200 workers, and you have to tell it what nodes, what GPUs, what threads you want for every worker. So this is loading the default configuration for Parcel, and that's just to run on local threads where you're executing the script. But of course, and I should say, I have a bunch of examples here for different patterns of workflows, and during the breakout session, we can go over these if this is interesting to you. But what we want to do is instead load a config that tells it how to use Polaris compute resources. So you would want to replace in those programs something like this, but you need to create this Polaris config. So we have here in these materials an example config for Polaris, and I'll just show you this code. And in the minutes I have left to discuss Parcel, I don't have time to go into all of the details in this config, but I will just mention that we would recommend using the executor, that is a high throughput executor. You need to use the PBS Pro provider because it needs to be able to communicate with Polaris's scheduler, which is PBS Pro, and then the MPI exec launcher. Those are a few things. And you'll notice in here, there are things like your account, the queue, the wall time. So all the things you would put into a bash script to submit a job to the queue, you need to tell Parcel, because what Parcel is going to do, and I will just set this running. I need to go to, I don't know. All right, we'll go to this one. I'll set this running while I talk. It's going to create for you a bash script and submit it to the queue and return a result. And actually, it ran so quickly, it may have, okay, so you can see here, I have this Parcel high throughput job on the queue. So that was just created by me running that Parcel Python script. And the particular program I was running was this script, Hello Polaris. And what this does is it creates a bash app that wraps around a compiled executable called Hello Affinity. This is from our Getting Started repo, where we have a bunch of programs for all our machines, little test programs you can run if you want to just figure out how to compile things and run on our machines. And what this does is Hello Affinity just reports what GPUs and what CPUs it has access to. I configured my Polaris config to run 4 workers, 1 on each GPU of a single Polaris node. And I did this by this available accelerators equals 4 command. So what then this program does is it runs 4 tasks, and Parcel should place each of these tasks on a different GPU on a Polaris node, and then run hello affinity, and then print the result. And that's what happened here. So you can see these little blocks of code. So we've got to affinity and beyond. That's the result of hello affinity. And you can see here, they all ran, this n name is the node name, that's the host name of the node. So they all ran on the same node. But then if you look at this UUID of the GPUs, you can see they're all unique. So it did in fact execute hello affinity in parallel on 1 GPU on a single Polaris node. And it also assigned CPU threads, et cetera. And in the breakout session, we can talk more about creating these settings to tell Polaris, tell Parcel how many workers to run. So this created 4 workers. If you want to create more workers, you can increase the number of nodes that Polaris has access to in a variety of ways, depending on the elasticity that you need in your workflow. And I can talk to you more about details of that. Okay, I'm gonna then go back to my slides and switch gears. The next tool we're going to discuss is Globus Compute. Okay, and Globus Compute is also a tool created by Globus Labs, and this allows users to launch applications remotely from a laptop or maybe another machine, maybe a facility, an experimental facility. Maybe you have an experiment throwing out data and you want to ship it to ALCF and run compute tasks on it. So this is an option for that. We'll talk about this more, but it's actually built on top of Parcel. So that's kind of why I'm talking about it next in this progression. So it looks a bit different about how you have to write functions. However, when it gets executed on the machine, you'll see it's actually just running Parcel locally on Polaris. It does require, so you can launch applications remotely, but it does require some setup beforehand on Polaris. You have to create what's called a compute endpoint on your target machine. So you may have heard of the Globus service as a data transfer service, and you might have heard endpoint mentioned. There are 2 types of endpoints in Globus. There's transfer endpoints, that's for transferring data with grid FTP. And then there are compute endpoints. And those are things that the facility won't set up for you. You have to set it up, because what it will do is it will start a process on a Polaris login node that will, on your behalf, submit jobs to the queue. So those have to be under like your account. So you have to create the compute endpoints and run them. And I should mention, Globus Compute has integrations with something else called Globus Flows. And I know we're going to have a Globus session in the afternoon, and it's probably a good opportunity to talk with them about how that works. I won't discuss that here today. So we'll go to the Globus Compute demo. And again, I'll switch gears. And we'll go back up to workflows and go to the Globus Compute section. And again, there's some setup that involves installing modules. Again, you can install the modules you need with pip, both on Polaris and on the remote machine where you're running. And then you need to set up and create an endpoint. And I actually already created an endpoint. So kind of like a cooking show. Some of this is baked in stages. So in this environment, I have a command line tool called Globus Compute Endpoint list. So I can call this. And what this should do is lists the endpoints I have set up on Polaris. To create an endpoint, you have to use a configuration, and I have a sample one here that will set up workers in exactly the same way as the parcel one I just discussed. So, but rather than express as a Python object, it has the format of a YAML file. But basically, to set up your own endpoint, you would run globus compute endpoint configure, and then you would pass it your configuration endpoint, and then give it the name you want to give it. And then once you've configured it, you need to start it with the same tool, globus compute endpoint start workshop endpoint. So you can see here, I have a couple of endpoints on Polaris for different things I'm doing, but I have this workshop endpoint that is running, it's in a state running. So you can see all the endpoints, their status, and then these unique IDs. The IDs are important. You need to copy that, and you're gonna use that on the local machine where you run your functions. So you have to, like, on your local machine, you're gonna be communicating with the Globus service, and you have to say, run it on endpoint with this ID. And so that's how it knows. And so I have here a shell. This is not on Polaris, this is on my local laptop, Oberon. And I'm in a directory with a copy of the workshop repositories, and we have a little script here that will run this function, add function, so it adds two numbers. And you will have to paste in your endpoint ID, but I have a version of the script where I've already pasted in my endpoint ID. And what it will then do, you create an executor object, and then you just run executor object submit your function and any objects. So the executor object knows your ID, and what it returns is, again, a future. We're back to futures. And what I include here is this print statement, and I will just start this one running. What I have included here is this print statement that blocks on the future. So if I go back to a Polaris shell, I can do qstat, and you can see I have a job in the queue, so it hasn't started running yet. So, okay, so maybe we might be waiting, but this is the fear of doing live demos. But essentially, what this endpoint, oh, I know why, because I submitted it to the debug queue. So if you ever need to change anything about your endpoint, if you look in your home directory, you will have this hidden directory, globus compute, and then workshop demo, workshop endpoint, and then config.yaml. And you can see here, it has a copy of my config, and unfortunately, I forgot to put in the workshop demo, so we'll just be waiting here. But what I can say is what should happen once this job gets picked up is it will execute this adder function, and the result of 5, or well, 5 plus 10, 15 will be printed to my shell. So this is like a way in which I can run a function from my laptop on Polaris. Okay, so that's just submitting a function I have within the script. It can be useful instead. Sometimes you have functions you want to run many times. So you can also register the function with the Globus service. And in the same way the endpoint has an ID, then your function will have an ID. And then you can just call that function with the endpoint ID and then the function ID. And you don't have to have it like in your script every time. So this is showing you two things. One, how to write a Globus compute function that wraps around an executable, and how to register it with the service. So this script will not actually run the script. It will run the function. It just registers it with a service. So this function, hello affinity, again wraps around that same program, hello affinity, I was running before, and it does three things. It goes to a run directory that I specify as an input, and that is on the file system of Polaris, not my local machine. So you have to make sure when you run this that it's a valid path on Polaris, on the Polaris file system. It then takes a command, which is just calling this program, hello affinity, and it runs it as a subprocess with the subprocess library in Python. It then returns standard out and standard error. It will then write the standard out and standard error to files on the Polaris file system. So you'll have these files in whatever run directory you specified there. And then it will also, if it runs successfully and no exception is returned, return the standard out and standard error as strings to you at wherever you are on your local laptop. So they'll print the standard error and standard out to files on the file system and return them to you as strings through the function call. So one thing to note here, this program uses a couple of modules, OS, subprocess. It's really important that you import those within the function itself, because what happens when this gets registered with the Globus service, the tool will serialize this function, ship it off to Globus. Globus, when it has a task to run with it, will send it to whatever endpoint is running it, where it gets deserialized. So it has to contain within it import statements for any function, any library or module that you're using. So you should not put these import, subprocess, and OS outside of it within this script, if that makes sense. And so then what we do down here is create a Globus client, a Globus compute client, and then we call this register function. And what that returns is an ID number. Let's go up to Globus compute, and I will just run this quickly. Register function, and what will be returned is the ID of my function. So you should save this. And then this last example will show you how to run Globus compute with a registered function. So again, you'll have to paste in your endpoint ID, your function ID, and then you create an executor with the endpoint ID. And then you can, in this example, we create 4 tasks that run this function, hello affinity, in different run directories, and we submit this to a registered function, and we have to pass the function ID as an option here. And then it's again, what this list task contains is a list of futures. So it is important for you to include in the script a blocking statement on the future results, which I do with a print statement here. And you know what? I think this is not going to return. I think I'm still stuck in the queue. But what I can do is, well, I guess I will maybe just leave that there. But this maybe does illustrate one important feature of some of these tools that use Python concurrent features like parcel. Oh, here we go. It returned. So it returned 15, and then I'll be really quickly run this other one. And hopefully my job is still active. Okay, so we've run this here. So again, this is on Oberon, and what it printed was first the results, which is just the return code, the standard out, and then the standard error. And you can see again, like all of these GPU IDs are unique, so it ran on the 4 different GPUs. And then what I also printed here is this, after I ran it, I also queried the client again and got some task information. So I can also, so there is, I guess I should say, this is a database model in some sense, because there is a database hosted on the Globus service where you can query and you can get information about the execution of your tasks. So this tells me things like the particular Python version that was used to run it. It tells me things about the completion time and I think also the start time somewhere. Yes, execution start, execution end, the result, and that it was a success. And so if you wanted to, query anything about your tasks, each task, like the function and the endpoint, has a unique ID that you can query in this way. Okay, and I will mention that this tool, this is just showing you how to throw a function basically at Polaris and run it. You likely would probably, if you're running remotely, maybe have some other needs in terms of remote execution, like data transfer or other things. And one thing I can point you to is this Globus Flows tool, which will take Globus Compute functions or actions and integrate them within a larger Globus workflow that can include things like data transfers coupled in concert with your execution. Okay, so I'm going much faster than I thought. That's probably not a good sign. Here we go. So the last tool I'll talk about is Balsam. So this is a little bit of a departure. So this is a tool that is developed here in the data science group at ALCF. It's been at the facility for many years, and this is a tool that we've used for managing workflows on ALCF machines and also deploying multi-site workflows as well. So Balsam is different from Parcel in that it uses a database model. So Parcel, when it has a list of tasks and their dependencies and how to run them, that description exists in memory during the runtime of the workflow only. What Balsam does is it saves the description of tasks, which in Balsam parlance, so I'm going to change vocabulary a little bit. Balsam calls tasks jobs, and then the jobs that you run on the scheduler, batch jobs. So I'll change my verbiage a little bit right here. When Balsam runs these jobs, what it does is it saves them to a database. And so the workflow progresses by querying this database that you interact with and that your batch jobs interact with. The database is hosted here at ALCF, so you do not need to set up your own database or anything. That's unlike some other database model tools like Fireworks, where you have to set up a MongoDB. This hosts a database on a server here at ALCF. So in order to use Balsam, you do need to be added to that server. So if you'd like to try out the Balsam tutorial, just drop us a line in the workflows breakout channel. Just post your username and we'll add you, and it should be basically instantaneous to test out Balsam. So Balsam can execute both external applications like compiled applications and native Python applications. It is also Python based, but it does have a command line tool that you can use to interact with it if you're not a Python person. The fact that you have this centralized server that's hosted at ALCF means that you can run it from anywhere, similar to Globus Compute. and run things on different machines, within one workflow as well. It does have integration for data transfers with Globus. And yeah, I mean, it's been used on basically all of the DOE machines and facilities. And I think one of the real strengths of Balsam is that it can very easily run a set of multi-node MPI jobs that have a diverse set of resource needs. So you basically just populate your database with jobs and you say, okay, this job needs 10 nodes, this job needs 5 nodes, this job needs whatever. You throw them all in the database, you start up a batch job, and Balsam will play this game of Tetris of fitting your jobs into the batch job dynamically. So yeah, now we will just switch to a Balsam demo. And again, I'm going back to the repository, and I'm going to switch gears to the Balsam demo. And again, there is setup that's involved. Is there an echo? No? Okay, there is setup involved. You will have to create, you can, again, we have a workshop environment that you can activate where everything is installed, but you can also install Balsam with pip in your own environment. To get set up, you do have to do some setup on Polaris. So the first thing you need to do is log into the server. So that validates your credentials with the Balsam server. And I've already done that, so I am not going to do that again. Where is the shell? Oh, it's in my home. But you would need to do this, and basically, and I should say, actually, I glossed over with Globus Compute because, again, I've already validated my credentials with Globus. With all of these servers that enable remote execution, or you're communicating with a remote server, you have to validate credentials with ALCF somehow. So usually with Balsam and with also Globus Compute, what it will do is spit out a URL at the command line when you run a command that requires credential validation. You paste that into a URL, it'll take you to ALCF where you can use your mobile pass token and log in. And then that will save a token on Polaris that then says, it's okay, processes started by this user accessing this remote database are validated, you can accept jobs from them. That will validate your credentials. You then need to set up what's called a site. So a Balsam site is two things. It's a workspace on the file system of Polaris, which will hold things like logs, setting files, and also outputs from your applications. But it's also a background process that starts on the endpoint, similar to the Globus Compute process, that will run in the background and communicate with the Balsam server on your behalf. So I have created a site already called Polaris Tutorial. So I'll just go there briefly. And you can see when you create a Balsam site, it will have these things. A data directory will data from your applications will be printed. A job template, which is basically just a template that Balsam used to write job scripts that it will submit to you, to the scheduler on your behalf. A log directory with various Balsam logs. A queue submit directory. This is where Balsam will store the submit scripts it creates. And then this settings file that has different settings. You may, over time, as you learn and use Balsam, want to tinker with that and change things. So I have to query whether my site process is active, and I can do that with Balsam site ls. And I have many Balsam sites. So let's see, hopefully this will execute. Okay, so I've got many on many machines here, but I'm interested in Polaris Tutorial, and it is not active, so I need to start it. So I'll do Balsam site start. And this basically starts this background process with this PID on this login node, Polaris login node 4. And if I do Balsam site ls again, it should tell me that my site is now active. Okay, good, we're good to go. So I'll go back up to where my scripts are. So the first thing you need to do, so I will say, I'll run a few scripts showing you the command line interface. So if you're not a Python user, there are ways you can interact with Balsam just through bash commands, essentially. But then I'll switch to the Python API, which is helpful in creating many jobs and loops and things like that. So this script will, let's see. And so first I need to create an application. Let's start there. So this application, hello. Applications in Balsam are expressed as Python classes rather than Python functions. So this is unlike Persil and funcex. So you have to write this class. And the two elements that are sort of required is your site that you're running it in. So this application will be registered in this site. It will be attached to this site. And then what's called the command template. And so I'm going to just focus on running bash commands in this tutorial, but there's a way of also running native Python as well. And so this application is just going to run echo, and it'll just say hello to whatever input we give it. So this is an input. You express it with this double curly brace. And then it will report what CUDA device that it sees. So you write this as a class, and then it's very important that you include this hello sync. So what this does, this command communicates with the Balsam server and registers. So this is like the equivalent of registering the function with Globus Compute. This registers the application with the Balsam server. So we need to register the function, hello. And it should just return silently, I think. And then I can do Balsam app ls. And it tells me, I have a few sites active right now, but it does indeed tell me hello has been registered in the site Polaris tutorial. So then this shows you a little script of how to run a Balsam app in a particular site, or how to create a job in a particular site with a particular app. So with the command line tool. So this is Balsam job create, and you're going to create an app in the site Polaris tutorial, a job in the site Polaris tutorial with the app hello. And then there's some other information you have to give it. You have to tell it where you want the outputs written. And so this is a path relative to the data directory in your site. You have to give it any necessary parameters. So that app took a parameter called say hello to. So we're going to say hello to world. And then you can also include things like tags. So we're going to tag it with workflow equals hello. And I will just execute that script. And at the bottom, it will also do this thing where it will print, it will query the database and list any jobs that exist in my site. So you can see here, it's queried, it created the job, and when it queries the site for the job, it says that it is in a staged in state. Sorry, I just made 2 jobs. Oh, well, we'll just see. We have two jobs, and you can see the previous job I created has progressed to another state called preprocessed. Jobs that are preprocessed are ready to run on compute nodes. So when you query the database for a job in Balsam, there's a few things to look at. There's the ID, the site, the app, the work dir, where outputs will be printed, but there's also this state. And basically, that's what the database is for. It basically tracks these job states as you run these jobs, and the states will change, and you can query the database and see okay, my job has progressed to job finished or it's failed, and you can query the database and see all of the statuses. Now we want to run it. So we have I'll just start this running. This script that runs a batch job on the queue that will run any jobs I have in my database that are tagged with workflow hello. And so you can see sort of intentionally, this looks a little bit like a qsub command. So the sort of initial philosophy of Balsam was that it's like kind of a way, it should look a little bit like the mechanics of what it is to submit a job by hand to either Cobalt, our old scheduler, or PBS Pro, the new scheduler we're using. But basically, you can see here that I indeed have a job now on the queue that is running. Queue launch is what by default Balsam jobs will be labeled as. So this was created by running this script. Balsam also has a way of like querying the batch jobs that it's tracking, and you can see here this script printed that out here. Sorry, let me make this a little bigger. So when it submitted it, it just said that, oh, well, it hadn't been running yet, but regardless, there's a tool you can use to query your queued jobs through Balsam as well. And if I do Balsam job ls, we can see that actually my jobs in Polaris tutorial have finished. So that's great. And if I look in the data directory, I'll go to Polaris tutorial, I'll cat data demo hello 0, or just job.out. You can see it prints the output of my application, which just says hello world, and it had access to CUDA device 2, so GPU 2 on that particular node. So shifting gears a little bit to the Python API. So this is showing you what it looks like if you just want to type bash commands or bash script, at the command line, or do bash scripting with Balsam. You can also run things with Python. So this script, create multiple jobs, let's see, will create 4 jobs, all running the app hello, tagged with this hello multi. So this is just showing you can create them in a loop in Python. The thing that's important here is you have to include this job objects bulk create. So this is the command, the Python command that registers your job with the database. That's, again, we're always communicating with this remote database hosted on a server. So if you run that and I query job ls, we can see that I now have a bunch of jobs in my Polaris tutorial site. I guess I created 8 of them rather than 4, but regardless, you can see here we've got a bunch now in my site ready to run. You can also create jobs with dependencies, and by giving it this parent ID when you create the job. So if a job has a parent ID, it will not run until that parent job has completed. And that's the way in which Balsam tracks dependencies. And you can see here, I've got a bunch of jobs that are awaiting parents. So then you can create batch jobs also through the Python API. And I'll just do that quickly. So this will create a batch job that will only run jobs with the tag hello deps, which were these jobs that are awaiting parents. So it should leave these other jobs untouched because I've told it just run things with this dependency. So we can see here that it's starting to run them. And again, because I've created this like dependency, they will run serially one at a time. But if I didn't have that awaiting parents functionality, they would run all at once. So I think I will just say that there's more functionality in this tutorial that you can look at. There are ways of like querying the database for performance information. You can do throughput plots. And in addition, there's an example running jobs on Polaris and on Theta GPU in a coupled way with job dependencies between the jobs on the two sites. So you can see a little bit what that might look like. And then at the end, I have this script that sort of provides a complete example of creating an app, creating some jobs, and running them on the machine. So let me just go back here. Okay, so I've gone through a couple of tools and sort of shown you what they feel like, what they look like. A lot of them are very Python-based, I do realize, and not everyone's a Python user. If that's a challenge for you, please come let us know. We can try and help. But it can be sometimes difficult to know what tool to use. And I would say that like every project has its own needs. And many of these tools have overlapping capabilities, but some of it comes down to personal preference, but there are maybe some nuances and differences in what capabilities these different things have. So if you want something that has remote execution of tasks, Parcel is not your choice. You need something like Globus Compute or Balsam. If you want something purely local and you don't want to be communicating with some server or anything like that, Parcel is entirely local, so that might be a choice for you. If you need to be able to run multi-node MPI tasks, Balsam does this really well. Parcel and Globus Compute have some functionality in this direction. They are currently developing a much more robust capability in this area, I know. So like stay tuned for those tools. Databases, so Balsam uses a database, Parcel keeps tasks in memory. Depending on what your needs or preferences are, that might be an advantage or a disadvantage, I don't know. Portability, so all of these tools can run anywhere. However, Balsam does require an ALCF account to validate with the server. All have integration for data transfers. And I mean, the last thing I will say is there's also workflow tools sometimes are applied. That term is sometimes applied to AI or ML steering tools, which I did not cover here. But we have many of those tools at the facility. You heard talks yesterday, I think, about SmartSim, but there are others, DeepHyper, Colmena, LibEnsemble. Many of these tools leverage workflow tools like Parcel and Balsam. And if you need assistance with those kinds of tools, come talk to us as well. So I have here just some resources on where you can get more information, more tutorials to run, etc. And I'm happy to take any questions. Thank you.
To begin, thank you. Regarding Globus, I can see the value of it. I noted on their website that there is a area licensing. Does the ALCF have that licensing, or is that something that we would need to take care of as individual orgs?
No, I think we cover that licensing. Is that right, Tom? Okay, we can talk more about that. It depends on what you need, I guess. But but in principle, most users who are just running work on our machines, I think it won't be a problem, but yeah, okay. But if there's other needs associated at other sites, we might need to talk about that, but we can work with you.
Thank you.
Yeah, sure.
There was another question. Okay, thank you. It's a very interesting talk. I have a question about global compute and probably also a question about Balsam. So for global compute, in principle, you can always wrap a batch job within the submission on the compute engines. When you return the results, do you return all the results associated with the computation itself, or just some information to the local machine, for example?
Yeah, I mean, I think there is, it's the information you can return to the local machine through the mechanism I showed you should be lightweight. It's not going to be terabytes of data. If you need to couple that with like a data transfer of a large quantity of data, you can do that through Globus flows. And we can show you an example of how to integrate Globus compute with Globus flows. So that is possible for, so the information that's returned by the function, I don't know if there's a limit, but I'm sure there is one, and it's, it should be small amounts of data. If you need to return large amounts of data, actually, we're going to have a talk about IRI workflows later, and that is a feature of those workflows. And we use Globus compute with Globus flows to do exactly that. So we can show you how what that looks like.
Okay, thank you.
Yeah, thanks.
Yeah, for workflow control, one of the problems on the shared machine is that since there's a resource allocation, often submitted workflow and some of the tasks may have to wait for the allocation of resources.
Yes.
That's a very unpredictable behavior.
Yes. Mm-hmm.
Anything to mitigate that kind of situation?
Yeah, so I did have a note on the parcel tutorial. So for a database model like Balsam, you will populate the database, and you'll tell the Balsam process to run something, and it should just all work, and it should, you can log off and you don't need to worry. For parcel, what you can do is use Screen, or there's a tool called No Machine. So yeah, that is something people running workflows in parcel locally on our machine. I usually just use Screen, but I know we've got a lot of users who use No Machine. That's kind of like a web GUI kind of thing that does that. And you have to keep, the process active. And so those are two techniques you can use. For Globus compute, I mean, I guess it would be a similar thing on your local machine, but I think in that case, what you should do is probably integrate with Globus flows, which is a more of it will keep sort of a record in a database of like how things are working. And I unfortunately in this talk couldn't fit all of that into this, but that would be an option for Globus compute, is to integrate with flows, and that wouldn't be necessary. But yeah, good question.
So any other questions? Okay, so let's thank Christine again and all of these morning speakers.